In this video, we're going to look at two related topics. The first one is differentials, and the second one is linear approximation. So let's start with an example. Let's suppose that we have a function like y equal 3x to the 6th plus 7x cubed. So we know how to take the derivative. That's just our familiar dy by dx. And we get 18x to the 5th plus 21x squared. So the new idea here is that these symbols, dy and dx, have some meaning on their own. They're called differentials. So dy is the differential of y, dx is the differential of x, and we can figure out dy just by multiplying our previous step here by dx. So let's try another short example along those lines to make sure we understand the idea. The problem is to find the differential of v, and what we're given is this formula for v, so it's actually the volume of a sphere, 4/3 pi r cubed. So what we could do is say, well, we know how to take the derivative in the usual way, dv by dr. The cube, or the third power, would come down in front, multiply with the 4/3, so we get 4 pi r squared. And then from there, we can multiply both sides by dr, which would give us this line here, dv equals 4 pi r squared dr. So there we go, we found the differential of v, which in symbols we call dv. So what we're going to be using this for in this video is the idea of error calculation. So next thing we're going to do is a little visualization of error. Let's jump to our second page of our notes, and we're actually going to start with a definition. So we're going to look at these three quantities here, and then beside that we're going to draw a picture just to get a visual. So we can represent a small change in our x coordinate in two different ways. We can either write delta x or we can write dx. So delta x or dx, they mean the same thing, small change in your x direction. dy represents the rise of the tangent line over a certain interval, and delta y represents the change in the y value. Okay, so let's draw a picture over here. Let's say we've got our x-axis, and let's say that we're interested in 2 points that are pretty close together on the x-axis. So we would say this is x, and then if we want to denote a small distance here, we can either use the symbol delta x or we can use dx, and we'll see in this section we use both, but I'm just going to go with dx for the moment, just for the sake of picking one. So if we want to show that these 2 points on the x-axis are close together, we could just call this one x plus dx. Okay, and then let's imagine that we've got some function. So here's our function, and we're interested in what's going on with the y values over that same interval. So we've got these 2 points that are on the curve sitting at those two different x values that we've specified here. So you can think about the difference in the y values here. You can say that is the change in y over that interval. So the appropriate symbol for that would be delta y. But the other thing we could do is we could draw the tangent line at that first point to the curve. So our tangent line might look something like that. And then we could think about, well, how far does the tangent line rise over that same interval? So if we look at our second x value there, the point where that would intersect the tangent line is about there. So that vertical distance there, that's what we would call dy. So we've got the rise of the tangent line over a certain interval, and we've got the actual change in y values over that same interval. So the idea that we're going to be getting at in this section, we can start to see it in the picture, is that when dx is small, meaning when our 2 points here are close together, the delta y and the dy are going to be approximately equal. So essentially we're going to be able to use dy to approximate delta y as long as our points are close together. So let's just call that a fact, and we'll see more details about that as we go through some of our problems. So just a little caution about the notation. So let's say that we have a function like y equal x squared. So x is the independent variable, and delta x and dx mean the same thing. So when you're talking about your independent variable, delta x and dx, they just represent a small amount of change in that independent variable. Whereas y is our dependent variable. So I'm just going to underline these important words here. So x was the independent variable, delta x and dx mean the same thing, whereas y is the dependent variable. So that's just a fancy way of saying y is the name of our function. Y is our function. And for our function, the delta y and the dy are different. We've got a function, f of x, given to us, and we're going to compute those two values for a given x value and a given dx value. Okay, so the point here is when we say f of x equals x squared plus 2, that's the same thing as saying y equals x squared plus 2. So imagine here's our parabola. Imagine here are two x values that are pretty close together. So the first one is our x value 1, and the second one is x plus dx. So 1.05, dx just representing that little change that we've made in the x direction. So moving from 1 to 1.05. So the dy represents the rise of the tangent line over that interval. So that's going to be our dy there. And the delta y represents the actual change in the curve. So delta y looks more like that. Actual change in the y coordinates over the curve over that particular interval. Okay, so let's calculate both those things. dy is the easier one to calculate. To get dy, you just go, well, dy by dx in the usual way would be 2x. And then you can rearrange that and you can say that means dy equals 2x dx. And we know our x value is 1. We know our dx value is 0.05. So if we plug all that in, we get 0.1. And that gives us the rise of the tangent line over that interval. We can think about delta y. Okay, so what do we have to do for delta y? Well, we're talking about subtracting one value of the function minus the other value of the function. So if you think of this as our delta y here, you're subtracting f at x plus dx minus f at x. So just think of it as going f at your bigger x value minus f at your smaller x value, just to get the difference in the f values, or difference in the y values, if you want to say it that way. Okay, and let's remember x was 1 and dx was 0.05. So in other words, we're saying just take the difference of f of 1.05 minus f of 1. And I'll just write down what our function was because we can't see that point on the screen right now. So f of x was x squared plus 2. Okay, so if we sub 1.05 into that, we get 1.05 squared plus 2 is the y value at the second point, and then subtract off the y value at the first point, we would have 1 squared plus 2. So if we put all that into our calculator, that comes out to 0.1025. Okay, so let's just label these two things, put a box around the second one here, and just make sure we understand on an intuitive level what's happening. So we could say the dy here, that's the approximate change in y. It's actually the rise of the tangent line, and that gives us an approximation to how much y is changing over that little interval, whereas this is the true change in y. So you get the true change in y just by going, what's your y value at your second point minus what's your y value at your first point. So the whole point of what we're trying to accomplish in this section is that dy is going to do a pretty good job of approximating delta y as long as our 2 points are pretty close together. So in other words, as long as dx is a small number, dy will do a pretty good job of estimating what delta y is equal to. So our problem here is to approximate delta y using dy. We know what our function is. Y is the square root function. We know what x value we're starting at, and we know how much x is changing by. Okay, so here's how we would approach this. We would say delta y is going to be approximately dy. That's valid whenever dx is a small number. And then let's figure out what dy is equal to. So if you wanted over on the side, you could say, well, dy by dx is equal to 1/2 x to the minus 1/2. And then that way, that would let you rearrange this to say dy is equal to 1/2 x to the minus 1/2 dx. So I just do that part over on the side, sort of optional. You can do it mentally if you like. So then we come back to the flow of the problem and we say, well, that's approximately equal to 1/2 x to the minus 1/2 dx. So I'm continuing with the approximately symbol because we're reading this as delta y is approximately equal to this. Okay, and then let's just plug in some numbers here. We'll plug in our x value and our dx value. So we're going 1/2 4 to the minus 1/2 times 0.1, and then you can type that into your calculator, and that comes out to 0.025. So this gives us an estimate of how much our y value is changing along this particular curve if we start at this point and then we just step this distance over to the right. And this is exactly the sort of calculation that we're going to need when we do error estimates. So sphere's radius is measured to be 2.500 centimeters. If the true radius is 2.512 centimeters, estimate the error in the volume. Okay, let's see if we can pull some of the values out of the question. So we'll use r for the sphere's radius. And when you talk about the measured value, think of that as your starting point. That's what you measure. So that's your starting point on the curve if you were imagining this visually. Okay, and then we need a sense of how much r is changing. So you can think of this as the error in r. It's how much we're actually off by. And the way you get that error is you take the true value minus the measured value. So the true value 2.512 minus the measured value, which was 2.500, gives us an error of 0.012 centimeters. And what we want to do is estimate the error in the volume. So let's think about a symbol for the approximate error in the volume. That would be dV. So dV, if you want to say it in words, it's the approximate error in the volume. Whereas, just for reference, remember that delta V is the true error in the volume. But since the problem says estimate the error in the volume, it's clear that we want the approximate error in the volume. So it's dV that we're looking for in this problem. So as an intermediate step to getting dV, if we wanted to do this in a logical order, what we might do is we might write our dV a little bit further down on the page just to give us room to do some calculation. What we need to start with here is finding just a formula for the volume. We're talking about a sphere. So the volume is 4/3 pi r cubed. And then if you like, you could write dV by dr is, well, the 3 is going to come down in front. You have 4 pi r squared. And then you could rearrange that to get dV equals 4 pi r squared dr. And that's what's going to allow us to figure out our approximate error. So we're ready to plug everything in here. We're using the measured value for r, so 2.500 squared. And then dr just represents the error in the radius, which we calculated as true minus measured. So 0.012, can plug that into our calculator, and it comes out to about 0.9425 centimeters cubed. We know it's centimeters cubed because it's a volume measurement. We're talking about how much is the volume off by. So that's an example of how we actually use differentials in error analysis. So let's talk a little bit about why we need to use differentials as opposed to just calculating the true error in the volume. So why do we need to use differentials? Well, let's talk about our notation a bit here. If we say absolute error in radius, then we're just going to call that dr. Whereas if we wanted the relative error in the radius, we would take the absolute error, which is dr, and we would divide that by r. So you take your absolute error and you divide it by your measured value to get your relative error. So now let's think about what would happen if you calculated the relative error in the volume. Let's say we're continuing the previous example. So we're talking about the volume of a sphere, let's say, and you wanted the relative error in volume for that sphere. If you follow the same process, you could put dV on top. So that's your approximate error in your volume, and then just divide by volume. And that would give you a relative error as a percentage, right? So you could say like 2% error or something like that. So let's actually go through this part of the calculation and see what would happen. So from our previous example, we know that dV for the sphere would be 4 pi r squared dr. And then if we divide that by the volume of the sphere, we get 4/3 pi r cubed. So let's see if we can actually simplify this. I'm going to cross this part out and we're just going to try to go through the details here of simplifying this. So the 4's would cancel, the pi's would cancel. You could cancel an r squared, so that would leave you with just an r on the bottom. And then you'd have a dr on top, and you've got this 1 over 1/3. So that 1 over 1/3 becomes a 3 on top. So you've really got 3 dr over r, or you could say 3 times dr over r if you wanted to write this in the most sort of suggestive way. So what this is saying is that whatever your relative error in the radius is, let's say it's 1%, the relative error in the volume is going to be exactly 3 times that. So if your relative error in the radius were 1%, relative error in the volume would be 3%. If your relative error in the radius were, 8%, your relative error in the volume would be 24%. So that's pretty interesting that the relative error in the volume comes out exactly 3 times the relative error in the radius. And then we could ask, well, could we actually predict why it's actually 3 as opposed to some other number like 2 or 4? And actually this 3 here, I'm going to highlight it a bit more. This 3 actually has physical significance. It has to do with the dimension of the sphere. So if you were doing a 2-dimensional area problem, you would have found a 2 in this place. If you were doing a 3-dimensional volume problem, you'd find a 3 in that place. So the multiple by which the relative error in the volume relates to the relative error in the radius has to do with the dimension that we're working in. So those connections there are what make it really useful to be working with differentials. This is why we want to work with dV as opposed to delta V. So you could imagine an alternate universe in which you, for whatever reason, didn't want to use calculus and you said, forget it, I don't want to work with dV to calculate the error in the volume. I want to calculate the true error in the volume. So you would be working with delta V instead, no calculus required. The problem is if you do that and you calculate your relative errors that way, you take your delta V, which is your true error in your volume, and you divide by your volume. You get some number. And then you could do the same thing for your radius. So what's your error in your radius divided by your measured value for your radius? Now you'd get these two numbers and there would be no predictable relationship between them. Like for example, if your error in your radius is, let's say 2%, now your error in your volume might be something like, who knows, it could be something like 6.21% or something. So no nice relationship with the 2%. And so that makes working with the actual error or the true error a bit less practical. It's certainly not as beautiful as working with the approximate error. So bottom line here, the question was, why use differentials? And the answer is because there's a really nice connection or predictable connection between the relative errors in the radius and the volume if we choose to use differentials to do our error calculation. So here's our problem. We're given A equal pi r squared. Okay, so that's the area of a circle. We're told that dr over r is 0.02. So this is actually the relative error in the radius. In other words, we've got a 2% error in the radius, you could say. And what we'd like to find is dA over A, so that's the relative error in the area. So anytime you have d something over that same something, you're talking about relative error, and that will be expressed in a percentage, like 1% error or 5% error, etc. All right, so what we're trying to find here, dA over A, we might as well start by trying to find dA. So you could start the problem fresh by going dA by dr. That's just our usual derivative. So take your area formula here, take the derivative, you'd have 2 pi r, and then you can rearrange that to get dA. So just multiply both sides by dr, you'd have dA equals 2 pi r dr. Okay, so now we're close to what we're looking for. We actually want dA over A. So on top, we put our dA that we just calculated, 2 pi r dr, and on the bottom, we put the area formula, which we were given in the question, so pi r squared. And then the idea is that at this point, there should be a lot of cancellation. So pi's will cancel, one of the r's will cancel, so that will just leave us with an r on the bottom, and then we can rewrite this a little bit more nicely. So we've got 2 dr over r is one way to write this. But because we were given the value of dr over r in the question, a better way to write this would actually be 2 times dr over r. It's the same thing, but just a better way of writing it, because then we can sub in, because we were told in the question dr over r 0.02. So at the end of the day, here's our answer, 0.04. So I'm just going to write that out in words so we can see that on the screen. So we're saying 2% relative error in the radius implies or leads us to a 4% relative error in the area. So that is the beauty of using differentials for error calculations. So we said in this video we're going to look at 2 different topics. The first one was called differentials, so we've covered that. And second related topic is called linear approximation. So let's take a look at this formula here. I'm going to put a star beside it because we're going to use it in a couple of examples. So the statement says, let A be a number near x such that f of A is known. From there, we get this formula, which reads f of x is approximately f of A plus f prime of A times x minus A. Okay, so let's understand a little bit where this formula is coming from. We're saying A is a number near x. So on the surface, it makes sense that f of x would be approximately equal to f of A. But how much are we going to be off by? Well, there's going to be a little bit of error. So you can think of all this stuff here as being the error. Okay, and how do we calculate error? Well, we saw that in our discussion of differentials. Basically, this stuff here is going to be the differential df. And how do you get df? Well, you take f prime and you multiply by dx. It's like our little bit of error in x. You can think of that as dx. So that's intuitively where this formula comes from without going through, without deriving the formula. We just want to sort of get an intuitive sense of where it's coming from. So this formula, if we want to refer to it, it's called a linearization. Specifically, it's called the linearization of the function f of x at the point x equal a. And that formula is valid as long as x and a are relatively close together. So there's no hard and fast rule of what it means for x and a to be close together. A more rigorous way of saying this is just that the closer x is to a, the better this approximation is going to be. So let's try an example of this formula. So there are going to be 2 parts to this problem. Part A, we're going to find the linearization of f of x equal x to the 4th at x equal 2. Okay, over on the side, I'm going to write out our linearization formula from the previous screen. Always good to write formulas out a couple of times just to get used to them. So the formula is f of x is approximately f of a plus a little bit of error. And the error looks like a derivative, specifically f prime of a, times a little bit of change in the x value, which will come from x minus a. So that's our formula there. And so first thing we might be wondering in this problem is, what is our a value? So the a value is actually whatever number is sitting here, really written in the form x equal a. So whatever number you've got x equal to is actually the a value that you're going to use for the approximation. So we're going to say a equal to. So a couple of the numbers that we need to calculate then, we're going to need to know f of a, and we're going to need to know f prime of a. So let's get both of those calculated. Okay, so f of a, or in other words, f of 2 in this problem, is what we get if we put 2 to the 4th power. That's going to give us 16. And in order to calculate f prime at 2, we need to calculate f prime. So f prime of x is 4x cubed. And that means if we plug 2 in there, we get 4 times 2 cubed, in other words, 32. Okay, so there we go. We got our 2 values that we need. And then from there, we can just plug into this formula that we've got on the right side. So I think for clarity, I will write out the formula again. F of x is approximately f of a plus f prime of a times x minus a. And what we're going to do is we're going to sub a equal to into this. So, okay, so on the left side, we've got f of x. Might as well just write x to the 4th. So that's what we're trying to approximate here. And we're saying that's approximately equal to f of 2. Okay, well, we calculated f of 2 to be 16. And then we're going to go plus. Now we need f prime of 2. Okay, we calculated that to be 32. And then continuing to sub in, the x just stays in x, and the a is a 2. So we're saying x to the 4th is approximately equal to 16 plus 32 times x minus 2. Okay, now a good thing to write down is that this is valid for x values near 2. So if you use this approximation for an x value like 1.95 or 2.1 or something, then it's going to give you a pretty good approximation to what x to the 4th actually looks like. But if you tried this for, say, x equal 100, 100 to the 4th is not going to look at all like the right side of this approximation. Okay, so let's try part B here, and this is where we'll convince ourselves that this linearization process actually does something useful for us. So part B is to approximate 1.98 to the 4th power using what we did in part A. Okay, so the idea of what we're going to do here is we are going to sub x equal 1.98 into our approximation above. So I'm just going to put a box around what we had as our final answer above. We're going to sub in here, and that's going to give us our approximation. So we're saying 1.98 to the 4th is going to be approximately equal to 16 plus 32 times 1.98 minus 2. So you can take that to your calculator. You can, that comes out to about 15.36. And if you want to confirm whether this linearization process really works, you could just directly type 1.98 to the 4th into your calculator and figure out, does that work? And the answer is, yeah, it does. It's just off by 1 digit, I think, in the second decimal place. So it's quite close. So what this linearization process allows us to do is to take any function, could be a polynomial, but later on in the course, it could be something more complicated like a trig function or something like that. And then what are we doing? We're really approximating it by a line. So this right side here, it's just a number plus a number times x minus some other number. So that's just a nice line. It's easy to do computations with that. It's easy to do follow-up problems with that. And no matter how complicated your starting function is, there is a line out there that will approximate your function. It's just that that approximation will only be valid for x values near the a value that you used to build the line. And basically that comes down to the fact that the rise of the tangent line is pretty good at estimating the change in y values over short intervals. So I want to talk briefly about how we would use this linearization beyond this course. So it's something that you'll see in other courses, in other applications throughout your education. Let's just talk briefly about it to understand really why we care. So let's suppose that someone gives us a function like f of x equal x to the fourth. We know how to take a derivative of that. So the derivative is f prime, which is 4x cubed. And when we do this process of taking the derivative, what we're finding is slope of the tangent line, or we're finding rate of change of the function. Now, a little bit later on in the course, we'll think about the reverse process. So where we actually start with the derivative and we try to go backwards. So let me just do some highlighting here. So imagine someone now gives you this derivative and says, okay, your derivative is 4x cubed. What was your original function? So there is a way to go backwards and figure out that your original function was x to the fourth. And what that process of going backwards does is it helps us with calculating areas and volumes. So we'll be seeing that a few weeks later down the road in our course. Okay, so if someone gives you a relatively nice derivative like 4x cubed, it's easy enough to go backwards and say, okay, that means my original function must have been x to the fourth, or maybe even something like x to the fourth plus 1 or x to the fourth plus 2, because the constant would disappear when you take the derivative. So let's say that's easy-ish. But what if someone says, hey, your derivative is e to the x squared? And then they're asking you, what function did that come from? Well, that's hard. And that's hard not only because we haven't really studied that topic yet, but I mean, that would be hard for someone who had spent time studying that topic. It's hard because this is just a difficult function to work with. So there are many examples of functions that are difficult to work with where it's hard to understand what was our starting function. The way we get around this problem is we say, well, instead of working with a tricky function like e to the x squared, why don't we just use this process of linearization to simplify it? So we would turn this e to the x squared into a line. That's what linearization does. And we'd say, okay, that gives us the equation of a line that's valid, near the point that we're interested in. And then that way, well, since a line is just a polynomial, it's easy to go backwards. It's easy to find your areas and volumes and all the things that you care about. So that's just to give you some insight down the road as to how you use linearization in practice. I believe it's always easier to learn topics when you have a sense of how you would use them. So the problem is to estimate the cube root of 8.3 using a linearization. So a couple of comments about this. First of all, sure, you could just go to your calculator and calculate the cube root of 8.3. Calculators can do that, but that would be missing the point of what we're doing here. So as we just saw in our previous discussion, often we use linearizations to simplify a function. So the point of this problem is to make sure we're comfortable with that linearization process. The second comment is that when we say linearization, this is also known as a linear approximation. So you may see that terminology as well. The two pieces of terminology are completely interchangeable. So I'm going to write down the linearization formula that we saw a few minutes ago, and then that will lead us to figure out what we need to solve the problem. So the linearization formula says any function f of x is approximately equal to f of a plus a little bit of error. And the error looks like a derivative times a small change in the x values. Okay, and this is valid for x values near a. We should be able to identify a function from the question. So the function that we're going to be working with is the cube root function. Okay, and then we need to choose an a value. A is usually a nice number. So meaning it's usually a whole number, usually something like 8 or 2. It has the added property that when we put it into our function, it gives us an exact value. Meaning in this example here, A is going to be a number that works out nicely when we put it into the cube root function. Our A value should be near X so that our linearization is valid. And the X value that we're going to be using in this problem is 8.3. So we might as well write that down. So X equals 8.3. So that would lead us to conclude that A should be equal to 8. So in these linearization problems, let's think of it this way. If we just talk very intuitively here, A is a nice number, X is a messy number. The point is that you're trying to approximate the function at a messy number, and you're saying, well, it's going to be this nice value plus this little bit of error. So in order to continue with our linearization then, we need to find f of A and f prime of A. So let's say f of A is what we get when we take our cube root function and we plug our nice number A, which is 8, into that. Okay, so that's going to give us 2. Then we need f prime of A. So let's start by calculating f prime of x. Okay, our function here is x to the 1/3. If we take the derivative of that, 1/3 x to the minus 2/3. And let's plug A into that. So f prime of A is what you get when you go 1/3 8 to the minus 2/3, and we'll do a little bit of algebra here. So let's think about this 8 to the minus 2/3. Okay, well, the third in the exponent takes the cube root. So cube root of 8 is 2. The 2 then squares that. So we've got 4. And then the negative gives us the reciprocal of that. So it's 1/4. If you just put 8 to the negative 2/3 into your calculator, you would get 0.25. And then you could say, okay, I recognize that as the fraction 1/4. So that way we can keep this exact and call that 1/12. Good, so those are the two numbers that we need for doing our linearization. And I think we're good to go. So I'm going to write out our linearization formula once again, just because it's easier to plug into when we've got it in front of us. So f of x is approximately f of a plus a little bit of error, which comes from f prime of a times x minus a. Okay, now let's start to plug in. So f of x in this problem is the cube root function. And we're saying that's approximately equal to f of a is 2 plus f prime of a is 1/12. And then we multiply that by x minus whatever our a value was, 8. Okay, so if the problem just said find the linearization, this is where we would stop. This is our linearization of the cube root function. And it's always good to write down where that's valid. So let's say valid for any x value that's near 8. So plugging in something like 8.2 or 7.5 is fine. But if you plug in something like 100, I would not expect this approximation to be very good. Okay, now let's scroll back and just see what the question was, because we're basically almost there, but we're not quite done. So the question was to estimate the cube root of 8.3 using a linearization. Okay, so the final step is now to sub in our messy number. So sub in x equal 8.3, and we get cube root of 8.3 is approximately equal to 2 plus 1/12 of, in the brackets, we'd have 8.3 minus 8. So in other words, just 0.3. And then if you like, you can put that into your calculator and just work out what this right side comes out to 2.025. So that's our estimate. And if you wanted to check whether you had done your work correctly, you could just go to your calculator, and of course you could just type in the cube root of 8.3, and you can check that, yes, it does come out pretty close. So before we finish this example, again, I just want to really emphasize how we would be using this. So this second part here, This part here, not really so useful in practice because of course we have calculators that can do computations like this. It really just allows us to check our work and confirm whether we've done a good job of approximating our function. So let's say it's really just a check. So this part here is really useful whenever we're working with a function that's a little difficult, like a cube root function, or later on, trig functions or exponential functions. Really useful to take a complicated function and just express it as a line. It allows us to do a lot of follow-up computations with areas and volumes and other physical quantities. So that's our video on differentials and linear approximation. Thanks for watching.